Okay. Okay, so moving on from this crap of cardinality and stuff is, so we are moving on to what we call matrices. So some of you are probably familiar with this. Some of you are not. Matrices turn out to be extremely useful in all kinds of applications. So that's what we're going to do. So what is a matrix? A matrix is not a movie. Well, it is a movie, but a matrix is a rectangular array of numbers. So often denoted, like here's an example of one. How about 1, 5, -3, 6, 2/3, 10. Or sometimes we use square brackets. Like this. So a matrix is characterized by its rows and columns. So, for example, 1, 5, -3, 6, 2/3, 10. I guess I should be a little cleaner with this. So this matrix I wrote up here is called a 2 by 3 matrix. Because it has 2 rows and 3 columns. Okay, so that's what a matrix is. Here's 2 basic examples. Now we have to write out what one looks like generically. What does a generic matrix look like? And by the way, I would be a poor teacher if I didn't sort of spell out, like, and some of you might know this from things in programming or other math classes, but storing numbers in vectors or matrices is a very, very useful thing, and it simplifies computation immensely. And in matrices, probably they popped up in the history of math and science a few years back, a couple hundred years ago. And I believe, and I would have to double check, but I'm almost positive that the reason they sort of were invented were to help aid in solving systems of equations. So for example, when you were in baby algebra classes, you might have solved an equation that had 2 variables and 2 equations, or 3 and 3. Turns out that those methods you learned in algebra class can be sort of made a little more efficient if we put things in matrices. And there's a whole class you can learn that. It's called linear algebra. Some of you will take it, depending on your majors. And it's a pretty cool class. It shows you all kinds of cool things. By the way, for example, that like Google, the search engine works is it's a big problem involving matrices. Matrices they're pretty much everywhere. All right, what does a matrix in general look like? Well, this is going to scare you. So in general, a n, or I guess we'll do a m by n matrix looks like, here we go, we'll call it M for matrix. And how do we list a bunch of generic numbers? Well, the way we do it is we do it like this. A sub 1, we use subscripts, but we have to use 2 subscripts instead of 1. Why do we have to use 2 subscripts? Well, let's think about that. Well, so right, one subscript represents the rows, the other subscript represents the columns. So the first subscript is telling you what row you're in. The second subscript is telling you what column you're in. So the entry A sub ij is the element in the ith row and jth column. So here we go with some more abstract notation that scares the you-know-what out of you guys. Now, luckily for you guys in this class, we will basically only consider matrices that have like 2 or 3 rows and columns. We'll keep them small. But in the real world, they can have thousands, if not millions of columns. That's I and J, yes. Right here, that's an I and that's a J. Okay, so what we'd like to do is if we have these new mathematical objects we call, and by the way, for those of you who are familiar with this, a 1 by n or m by 1 matrix is often called a vector. So this is, you might have something with 1 row and n columns. So maybe we'll call it V equals, I don't know, maybe V sub 1, V sub 2, V sub 3, V sub n. Or maybe you have, we'll call it U, it might be U sub 1, U sub 2, U sub n. So for those of you who have ever studied vectors in another math class or maybe in a physics class, we often call these things n-tuples or vectors. And there is a connection with the arrows, although we're not going to go into that right now. So essentially a matrix is a mathematical object, just like a number is, or a function is, or a shape is, or a graph is. And the nice thing about matrices is that we can perform arithmetic on them. We can define arithmetic that is useful. Like I can say matrix A plus matrix B equals hat or dog. That's a fine definition, but that doesn't help us solve problems. It doesn't make us make matrices useful. So it turns out we can define operations on them. So we can define useful operations on matrices. So let A and B be two M by N matrices. We can define their sum. By adding entry-wise. So if I take A sub 1, 1, A sub 1, 2, all the way up A sub 1, N, and then A sub 2, 1. I'm not going to fill it all in because it gets very cumbersome. And we're going to do an example in a second that shows this is actually very straightforward. You add them entry-wise, A sub 1, 1 plus B sub 1, 1. And then it's A sub 1, N plus B sub 1, N. So look, this notation I get looks very overwhelming. But when we go to the next page, you'll see how straightforward it is. So look, this is the definition, and I know it looks overwhelming. Let's just do an example, and you'll see how it's very straightforward. Say that again? Yeah, sure. Yeah. I actually caution, I shouldn't even write it down this way. This looks more scary than it is. You actually add matrices in what would be a very intuitive way. Has anybody ever done vectors before? A vector in here? No? Vectors you add and subtract in an intuitive way, but you don't multiply in an intuitive way. But it turns out the intuitive way isn't the best way to multiply two things. And we're going to find out the same thing with matrices. Are you good? Okay. No, thank you for telling me. All right, so let's just look at an example, and then suppose I have two 2 by 3 matrices, 5, -5, and 2, and then 1, 0, 6. Suppose I want to add this to 3, 10, 4, and then negative 25 and 13. So I just do each component. 5 and 3 is 8. Negative 5 and 10 is 5. 2 and 4 is 6. Negative 19, 5, and positive 19. And then I don't think it would take much to convince you that subtraction is very similar. If I wanted to subtract two matrices, ten minus 5 is 5, 20 minus 4 is 16, 30 minus 2 is 28. Does anybody have a question about this? Yes.
What happens if the rows and columns are different?
It's a great question. You can't. Right? Notice when I defined this, I said they have to both be the same size. So that's a good point. The point was, what happens if the rows or columns are not the same? So that's a very important remark. Addition, subtraction is only defined when both matrices are the same, have the same size. So the fancy word for that is dimension, but we're not going to get into that. But some of you may have heard of that before.
Can you go back to the example for a few seconds?
Sure, yeah. Do you have a question about it?
No, I just wanted to look at it.
Make sure you understand those negative numbers, particularly in the green one.
Okay, I'm good.
Sure. Any questions about this? Comments? So again, notice in these three examples, they both have the same number of rows and columns. All right, we can also define a product. So that's the fancy word for multiplication. So this only makes sense if A is M by K and B is K by N. So notice I used three letters. I used M, K, and N. This only makes sense if the number of columns of A equals the number of rows of B. So in English, not just symbols, in English, the columns of A equal, or I should say the number of columns, equals the number of rows of B. That's the only way that you can multiply. Now, a cool feature of matrices is many matrices that arise in like useful applications often are square matrices. They have the same number of rows as columns. So multiplication is usually defined in that, it's defined in that sense. So this is a scary definition. And it's not easy to write down. So what we're going to do is we're going to set AB, that's the product, to some matrix C sub 1, 1, C sub 1, 2. Now, it turns out that C is also going to be M by N. Oops. Now, here's where the scary part comes in. C sub ij, the ijth entry of C is, oh boy, here we go. Do not have heart failure. I repeat, do not have heart failure. We will do some examples and then you will go to the YouTube and the Google machines and you will ask them to show you how to multiply matrices. And it is much easier to understand this by actually multiplying freaking matrices. Do not lose your mind on what I'm about to write. All right. Whew. A sub I1, B sub 1j, plus A sub I2, B sub 2j, plus all the way, this pattern continues all the way out to the kth entry. Yikes. Now, I am not saying that you need to memorize this. That is a bad way to learn this. Do not memorize. Do not try to memorize this. What you should do, if you've had any experience with vectors, you'll notice that the right-hand side is a dot product. If you've ever heard of what a dot product is before. If you haven't, don't worry about it. The best way to do this is to do examples. I'm telling you, it's brutal. Learning this is, it's like it's the opposite of a drug. It makes things worse, not better. I meant like a real drug, not you street drugs. You get your mind out the gutter. Drugs are bad, except caffeine. It's good. Okay. So look, this is scary. I don't know an easy way to sort of to teach you how to learn. It's just repetition. It's repetition. You know, it's kind of like learning how to walk. You don't know. You just see everybody else do it, and then eventually you're like, okay, it worked. So let's start. Let's start in a simple case. Now remember, it only makes sense if these things are defined properly. So what I'm going to do is I'm going to do the following. I need the number, remember, I need the number of columns of A. Here's a cool thing right away. Think about numbers multiplication. 5 times 6 is the same as 6 times 5, right? Already you see that matrices don't have the same arithmetic that numbers do. Right away, you see commutativity might not even make sense, right? Notice we defined A times B. We didn't say that A times B is B times A. So there's a lot happening here. It's very much mind-blowing. Well, not necessarily. It can work with matrices, just not all the time. Well, that'll give us a homework problem. So let's start. I need the number of columns of A. So let A be this. Let A be 5, -2, 6. And let B be equal to 4, 10, and 20. So what I'm doing now is I have two matrices. There we can. 3 columns, 3 rows. This is perfect. So note A is 1 by 3. B is 3 by 1. Thus, AB is defined and will be a number. A 1 by 1 matrix is just a number. So what is A times B here? A times B is equal to 5 times 4. So we can even write it out just for fun times. Let's write it out. So what does our formula say? Well, if we go back to the previous page, if you will, I sub j. So let's start with C sub 1, 1, or A sub B 1, 1. So let's write it like this: A sub B. Well, we called it. Let's call it what we did before. We called it C. So let's call this the matrix C sub 1, 1. So what is this? What is C sub 1, 1? Well, it's A sub 1, 1, 1, B sub 1, 1, plus A sub 1, 2, B sub 2, 1, plus A sub 1, 3, B sub 3, 1, which is nothing more than 5 times 4 plus -2 times 10 plus 6 times 20. And if you do the arithmetic here, that's 20 minus 20, which is 0. And then 120. Now, there's 2 ways to do this. You can do it using this definition the way I just did it, but that's not, in my opinion, the easiest way to do it. The easiest way to do it in general is to sort of have some pattern that you go over. And here's what I mean by that. By the way, does anybody have a question about this before we move on? I know there's lots of subscripts and I know it's overwhelming. I don't know what to tell you. You just got to look at me and say, holy hell, if O'Grady did it, I can do it.
If you have a second row for A,
Yeah.
it would be multiplied by the second column.
That's exactly right. You already figured it out, right? Very good. You're seeing it. So Mackenzie started to see the pattern. What you do is you take the first row of A and multiply it by each column in B. Then you take the second row of A and multiply it by each column in B. Ah, see, there's a pattern. You'll figure it out. That's right. So let's look at an example. Look at this. All right. The hell's wrong with me? So let's illustrate that. That's a very good way of thinking about this. Now let's let A, B. Let's do something like this. How about 2, 5, 6, 4? And then we'll let B be let B be equal to 1, 9, -8, and 10. So here's what I'm going to do. I'm going to, so here's a pattern. So you take each column, each row of A, and quote unquote multiply it by each column of B. So let me write this out in this way. So if I take the first row is 2 times 1, and then plus 5 times -8. Now, what's the first row times the second column? That is 2 times 9 plus 5 times 10. Now I do the second row. It would be 6 times 1 plus 4 times -8. And then it's 6 times 9 plus 4 times 10. And if you do the arithmetic, you get -38. And you get 68. You get -26. 6 times 9 is 54. 54 and 40 is 94. So if my arithmetic is not wrong, there you go. Yikes! Woo! So in my opinion, this is the best way to learn how to do this by hand. Now, of course, calculators can do this very efficiently. Software can do it. But you should know how to multiply matrices. Now, I can do 30 examples. That ain't teaching you how to do it. You ain't learning. You need to go home and multiply these damn things. Dam as in protect water from falling. Not dam as in. I don't know what's wrong with me. I don't know what's happening to me. I don't. Okay, so we have some arithmetic on matrices. We know how to multiply and we know how to add and subtract. And then we wonder, are there matrices that actually do the same job as, like, think about numbers. If I add any number to 0, what do I get? I get what I started with, right? If I multiply anything by 1, I get what I started with. So we wonder, are there corresponding matrices? And it turns out there are. So the matrix 0 equals 0, 0, all zeros. Is called the zero matrix. So it plays a similar role to the number 0. How is it possible that it does this? It's easy. You could define a matrix that has all zeros. Take something like 1560. If I want to add it to 0, 0, 0, 0, what happens? I just get 1560. You guys, this is.
Oh, but it plays a similar role when you multiply by 1.
It looked like a what? That's because I spelled this. Looked like a 1, you said?
No, it plays this similar role of when you multiply by 1.
Yeah, and then what if you, well, we didn't get that far yet. And then what if we multiply this thing? Well, you're just going to get 0, 0, 0, 0.
No,
Is that not what you said?
it's not there.
Huh? Does anybody have a question about this? Okay. The square matrix, now I'm being very specific. What does square mean? It means rows equal columns. So the square matrix I, which is, we denote 1, 0, 0. It has zeros everywhere except down the diagonal. This guy plays the role of the number 1. And it's called the identity matrix. So any matrix times the identity if you do the math, you get 1, 2, 3, 4. You should verify that. And if you multiply it the opposite direction, you still get the same thing. What do you mean, how do you multiply by 0? No, because you're doing it wrong. Take rows and columns. Take the first row, right? You know, remember, it's not entry-wise. It's not entry-wise. Very good. See, you already forgot what you realized earlier. All right. And then we have 2 more definitions, and then we will leave you to get out of here. All right. So we can have matrix powers for square matrices. So what does, say, a to the k? A to the k would be a times a times a times a, k times. Now notice this only works if a is square, because you can't multiply unless rows and columns match. And this is true for k equals 1, 2, 3, etc. And a sub 0, by definition, is always just 0 matrix. So the same, it's very analogous to powers for numbers. and we are out of time. So I will end it here. I'll give you a homework on this. It's a lot. This homework's going to be a lot easier than the last one because it's just learning how to do arithmetic. So it's not proofs. Well, there might be one or two basic proofs. Anyhow, guys, thank you very much. I appreciate it. I hope you guys email me with questions and you don't get too stressed over the last homework. There's more to life than cardinality. Thank you, guys. Take care.